totally agree. The colors are way better, especially the comments. That's what's kind of ironic is like when you're reading the code, you want the comments to slightly fade a little bit, but then like when you're presenting, you want the comments to pop, and like the black background here just does not do well with this. So I understand. All right, hello Twitch people. Let me find my Twitch stream. I have to set this up with power because I didn't have power last time. Be ready to rock and roll. Connor nerd sniped me with a bit of a. With a description of how 365 went and how Jan doesn't know how some tools work. So I had to troll him and telling him I'd give him training on tools like EtterCap. All right. This. Okay, we'll be online in a second. One more power cord and we will be in business. Okay. As I'm getting set up, first question for the group assembled here, my experts and also the people online. So I see that, very happily see that some of you have started on the XNU IPC challenges or the Mach IPC challenges. You will see that there are more since the last time you saw this, maybe. I just added some more. I think all of these are now new. But for those of you that have done this, an honest answer of how annoying it was to not have a permanent home directory, but getting blown away every time. Okay? Like not amazing, but you kind of worked around it and got used to it? Okay with the command line, so it was okay? Yeah, I think I have a way I could do it, but it just, I don't know, it may be too much of a pain. I'm trying to, there's other things like more challenges and stuff I'd rather work on than deal with that, because I can like create you a permanent, or not a permanent, a semi-permanent Mac volume, like a 1 gig thing that lives on that server that's yours and gets mounted every time, I think. I'm not sure I can line it up correctly. And I'm also slightly terrified that once I enable practice mode and root, then you could like write set UID things there, which then I need to like fix and redact, and it just like is like a whole other complex things. Because for the next things, I want to be able to get to those stuff. So, anyways, if it's a massive pain, please let me know. I can prioritize implementing that, but I'd like more of have stuff to work on rather than necessarily have the environment to be super user friendly. Okay, but let me know. And Twitch is just not popping up. My Twitch followed live channels. There we go. Cool. Okay, nothing's thing. Okay, so this is, I'm gonna add some more to this module. I think I won't go too crazy. I was already thinking about going crazy, but developing this thing, it's like a choose your own adventure module. Like each of these little things I need to test, and I mean, part of it you test that you verify that it does work. So I have a confidence that it does work. But like there's a lot more craziness we can do about like sending ports from other things. But I figured this is a good enough like intro to how this stuff works. And the next, I'll add a few more to here of just about exploitation, of just like exploiting through sending port messages. And that'll be cool because this will be the first exploitation we're doing on Mac OS binaries. It should be very similar to the ROP. Again, remind me and let me know if there's tools. I mean, there for sure are tools missing, so I can make sure those tools are installed on the image. That should be no problem. Oh, the question was, how hard are these challenges? I'm scared to start. These challenges are, I don't know, people have done them. I would say they're not hard necessarily, but they really do force you to have a good understanding of these APIs and how they work and how, like, I also deliberately don't give you the part of this is also getting more experience at reverse engineering these things. So sometimes you need to disassemble it or look at the binary to see why it's doing things. Or for instance, I won't spoil it, but some people, of course, on the very first one, you'll have problems receiving a message and you'll get an error message and you'll look up that error message and you'll be like, this doesn't make sense, but it actually does make sense when you start thinking about it more based on what's actually going on. Similar to you, I also got those. This is how I know this. I got those same error messages. And what did I do? I started reading the kernel source code, looking for where that error message was returned. And then it kind of hit me of what the problem was when I saw where that was. So then logistically looking forward a bit more, today we're going to talk about important ports. So this is like, we didn't get to this, I think I hinted at this, of things that are very useful for these ports. And so this is like how to talk to kernel services that use Mach ports and what those services that they offer are. We're going to talk about that today, kind of like a applied use case. I think I will make another module with this because I think it'll be super fun. I think you guys will really enjoy some of the cool stuff you can do of like simulating these things, where as an attacker you get one of these special ports, and then how do you then use that in order to take over a process, or even, I don't know if I can do it. If there's some way I can do it with the whole operating system, that would be super cool, where you have to like break yourself out, but or exploit the OS. That'll be cool. Then the week after that, the next thing after that, I want to be dtrace. So dtrace is the best like debugging, tracing instrumentation. I have slides I'm creating about XNU introspection. So seeing what's going on the system is super important to do any type of exploitation. To be perfectly honest, I don't think it's going to be feasible for me to set up the ability for you to debug one of these VMs. Just because it would either require giving you access to 2 VMs, because the way you have to set up 2 machine debugging is like one machine, you set like boot args to tell the machine, hey, on a crash or on a debug interrupt or a trap, listen on this Ethernet port for any connections. And then on another machine on the same local network, you can connect to that IP address, and then you can start debugging from a second machine. But like setting all that up so that you could do it, I could probably do, but setting it up to where you could not mess with each other, I think would be a nightmare. So I just don't think that's possible in a semester. And even more so, I actually found that type of kernel debugging way less useful, especially on ARM hardware, because you can't modify anything. You can only set breakpoints. At least this could have been I guess it could have been user error. It could have been the OS I was using, but you could set a breakpoint, you could hit that breakpoint, you could not single step. So there was no like, every time you single stepped, you just like, it would blow up and you wouldn't get anything. But you could set a breakpoint, you could inspect memory, but you couldn't change any memory or change anything. And so you can do all of that stuff with dtrace, and it's better because it's scriptable. So it's a fantastic tool to learn. And I was vindicated because when you go look at some of the Google Project Zero write-ups and the exploits, a lot of them, like, they have accompanying descripts that the exploit authors have written that helps them do what they're trying to do. So I think that's a much more valuable skill that we'll develop, and that'll be very useful. Maybe in the future, in next class, we'll have debugging. So answer the question in the chat. Did I upload the slides to the site? Yes. So now the lecture from last week on Mach IPC is here, and also the slides are here, so you can check out all the slides from last week. I can also post the other slides. I'm not quite sure exactly where they should live because they're not necessarily tied to a module, some of the earlier stuff, but I'll probably put them on the syllabus or something. Any other class-related questions, or any class-related questions since I've just been talking? No, cool. All right. Oh, and I see a few people. Actually, do I know how many people? Some people have already started on the real world challenges, so good job. This now does work. This was the other thing that prevented me from creating challenges earlier, is getting this to work. It was working, and then we had a server reboot, and it was relying on DNS mask, which needed some feature that I could only do on the host, but Connor didn't want me to do that permanently because it doesn't make sense to do that for one challenge. So I had to Actually, this was a great use of using ChatGPT to create a DNS server that always replies with one fixed IP address to any query, which eventually solved it. But yeah, these are 3 real solves as far as I know. The one unintended solution that we know about is gone. If there's any more, let me know so we can fix that. But cool. Okay. Great. All right. So now let's talk about the important ports. There's no real term for this. I kept like Googling to see what the term is. I didn't ask ChatGPT. Maybe I should have, and it would have told me the actual term. But you could think of them as kernel ports, but that's not quite accurate but essentially they're slightly different. So basically, they're ports where the receive right is held by the kernel. So that means basically the kernel owns that port. And so they each, and just like we said, right, ports are just objects in the operating system. They don't have any like real object manifestation, but the kernel creates this and says, okay, this is the special port for this, and I have the receive right, and then whoever I give that send right to. Now, if you have a send right to that, well, you can interact with it, right? So you have a send right to that port. It means you can send messages, and the kernel will just do whatever that important port says that it can do. And because we know send rights can be sent to another process, they can be stolen. This is actually what a lot of exploits and jailbreaks, and I guess trying to think if I should be more precise with those terms, but I guess just to get all on the same page. So when I talk about a jailbreak, I'm usually talking about like an iPhone or iPad, basically exploiting, and it's usually not one bug. These are series of vulnerabilities that allows the jailbreaker to get total control of the operating system, to install whatever software they want, to do that. So you can think of it as like one exploit or a series of exploits. That's like a jailbreak. And so a lot of them actually will use these techniques, and we'll see why as we get through of why they're so powerful. So if we can get a send right to one of these ports, we can get a lot of control over the system. So the first one, and there's kind of 3 main categories that we're going to talk about here. One is for the host, which you can think of as kind of the machine. I didn't bring the book. The book has a very good diagram of the different types of ports, and a lot of them give you access to other ports. So there's a nice diagram in the book. I don't really know if I have the license to like take a picture of that and put it on a slide, so I didn't. I meant to bring it, but the book is huge and falling apart even after like a year of ownership, which also frustrates me for an expensive book. But anyways, I meant to bring it, show that because it's very nice. And I also couldn't find one online that I could link you to. So maybe we'll just have to draw our own diagram or something. But so there's 3 main ones: hosts, tasks, and threads are the main categories. And the host port is actually not a privileged port. This is just gives access to host level information. Almost anyone can call this mock host self. And we are going to, of course, as is our style, going to, I already made it here. I want mock host.h, and I will set, how did I change the thing? Load theme. Oh no, I don't know what we actually did. Was it solarized? Yeah, this was it. Man, it's so ugly. Okay. Whew, it's gonna take a little bit. Okay, everyone can see that in the back? Thank you. All right. Cool, so these are, the things we're looking at are technically MIG messages. So this is the message interface, or Mach. interface generator, message interface generator. It's basically a way to use these Mach host defs. It's a thing that defines like a way to call a procedure from user space, but using Mach messages under the hood. So these all happen under Mach messages, but for now, at least for these things, you don't really have to know about that besides getting a port. Okay, F4 is asking, is it fine to think of them as task ports? Not quite, because they provide different things. So we'll talk about them. There are a specific thing called task ports that are a port that if you have send rights to means that you can control that task. But we'll get there in a second. So anyways, so there's functions in here like host info, which gives you information about the host, host kernel information. This gives you information about the kernel version of the thing that you're running. Anyways, just basic information. You also from there get access to other ports. So there's things to say, hey, give me the clock port, and it gives you a clock port, and that's a very simple unprivileged thing that you just send messages to, and it sends you back the time. The processor set port, which we'll talk about in a second, and this IO master port, I think allows you to like list what kernel extensions are running and other types of things. The cool part is why is that like that? The cool part is the host priv port, and this does not stand for private, which is what I thought originally. It's privileged. So this is the actual like really cool port with security sensitive operations. You call the function host get host priv port. Why don't I have this? So you can reboot the system. You can wire in, I think, more memory. So the VM is virtual memory. There's stuff you can do to the virtual memory system. You can set the exception ports, which we'll talk about in a second. And why don't I have this on the slide? I obviously don't want this. Something like that. Anyways, only for root. So root is the only process that's able to actually access this this privileged port, and I believe, yeah. So this one's super important, and let's look at host priv because there's some interesting functions in there. The MIG stuff, don't care about that. Get boot info, so you can get information about the boot, reboot it, stats, the default memory manager, VMwire. I think this allows you to change virtual memory address mappings in the kernel and say like, I want this thing to map to this thing. And you specify a task that you want that to probably have happen to. Thread wire, so that's interesting. Probably manipulating threads. I can't remember what CPM does. We can check that. Getting access to the processors, the clock, kmod create. These are interfaces to create kernel extensions and load kernel extensions, but if I remember correctly, they are not used anymore. And the reason is because it used to be the signature checking for kernel extensions being loaded was done in a user space process. And that user space process would then do the checking, signature checking, and then load the kernel module directly through these methods. But these methods weren't doing any checking, so then root could easily just load in kernel extensions, and it was a bypass of the system integrity protection. These special ports is what we'll talk about in a second. There are exception ports we're going to get to the end, but you'll note that these will come up in several different contexts that are important. Let's see. VMwire. Isn't this the same thing we just saw? Mach VMwire versus VMwire. Ooh, caution. I love that. Okay. Who cares about this? Sizes of messages. All right. Cool. So then the special ports are kind of get around the problem of the bootstrap server. So this is something we saw last week when we talked about the Mach IPC, right? We need to like register with the bootstrap server in order to give our port to them that they can then make copies that, or sorry, not give our port, but give our send write to that port so that they can copy send writes and give them to anybody else. There's actually a fixed set of port numbers that you can just use, and the kernel knows that this special number maps to this specific thing, which is kind of cool. And again, the really interesting thing about all these things, and I'll try to bring it up when I can, is a lot of these have actually been used in bypasses and exploits. Because access to these things are so special, if they're not controlled correctly, then you have massive failure. So let's look at host special ports, my favorite special ports. Host special ports. So these are the host port. Port 1 is, so you can see here, these are them, host port, host priv port. So this is when you like ask the kernel, I think, for host priv port, it just returns 2 is probably my guess here. But this way you can just like send messages to this port, or try to without that. Host IO main port and host max special kernel port. So anyways, they basically have reserved the first 7 numbers for them to use, and then they have a bunch of other ones. The cool thing is almost each of these is used by a different daemon on the system. So this is how basically the kernel like delegates special things to them, because they have access to these ports. And I believe launchd, when it sets these, knows to send this certain, like give this port number to these things. And why this is important is if we look in host privilege, so for instance, if we look in here, there is a AMFID. I think one of these is controls security properties. Let's look this up real quick, because yeah, so this AMFI checks file integrity, Apple mobile file integrity. This makes sure you don't like modify a like launchd or something like that. So it does checks. And so this is something that's very important, this AMFID. And in host priv special, not only can you swap, so you can, if you have access to the host priv port, which root does, you can set a special port to point to another port. So you can tell the kernel that AMFID port now points to this Mach port that I am in charge of, right? Because these are just numbers. These are the port numbers, and the operating system has to map them, right? The port name, or sorry, they're numbers, but they're actually the port name. So they map to some port object that somebody else has the send write to. So as root, and if you can get host privilege, you would then be able to tell the kernel, anybody that's sending anything to AMFID, send them to me on this port. And then you start reading and responding and saying like, yep, the system integrity is good. This file checks out, this file checks out, this file checks out, which would then allow you to more permanently jailbreak the system and then elevate from root, just bypass system integrity protection, all these other protections of the kernel. Because again, we didn't go into it in details, but it's important to remember that root is severely limited in both Mac OS and the iPhone. So even if you have a user space to root local privilege escalation, you still can't modify the operating system kernel. You can't modify special system files. There's a lot of things you actually can't do. And so these are kind of cool ways around that people have found. But they have since, I think now you can't actually set any of these ones specifically for this. Okay. All right. Wow, this is going to go way faster. Last time, like 20 slides took like 2.5 hours, but that's okay. We'll just start reading code. That's my plan. Okay, so we had this thing, and we said that so a process is a concept from BSD. Mach does not have any notion of a process. All it has is a task. And a task has a thread, something that is running inside the task. So you can think of the task as like a container there. So there has to be like some mapping there between a BSD process and a Mach task. And let's actually, this is a little bit of a detour. It doesn't go with exactly what we're talking about, but I specifically want to bring this up so we could look at the kernel data structures for these different things. So we could start seeing how these two lands of Mach and BSD start to like come together. So let's see. These are all kernel stuff. We can tell because there's the OSFMK in there. And we want temp build XNU 12.5. This, let's go to BSD land first, sys proc internal -h. And what we're looking here is some struct that is defining this. And what we're going to hopefully look for, and if maybe I just look for struct. Oh, it's cool. It's so this is a process group. We know there's a struct proc because there's something there. Aha! Description of a process. This structure contains the information needed to manage a thread of control known in Why is there a reason that there's a star there? Is that like, are there other things than Unix? Huh? Unix, Ufox, like I don't know, Unix. Anyways, that's weird. I'm sure there's some weird historical reason for it. It has references to substructures containing description of things that the process uses, but may share with related processes. The process structure and the substructures are always addressable, except for those marked proc only below. Okay. So we'll get into this eventually, but there's like pointer signatures that get used. And this would be our task. So we actually got there very easily. But the very first thing, so actually the very, very first thing is the process list. I don't think we'll go into it now. If you're familiar with the Linux kernel, there's a lot of similar insanity with macros here to define structures in structures. So if you want a list of, let's say, procs, you define this list entry proc called plist. So this is the struct that your list entry is of. And this plist, I think, then makes sure that you can do like list next. There's other macros like getting the next element from the list if you have one, iterating over it, all these kinds of things. These are all meant for this. Yeah, cool. And if I had to guess, is that a good guess? I don't know, maybe not. I guess that this pointer is probably signed and protected so that way you can't overwrite the proc list with a pointer to the kernel's task and then pretend to be the kernel. It's probably my guess is why they do this specifically. But here, so this is going to be a pointer to the task for that. And then let's go look at that. We're looking at pointers, right? So we found the proc struct. Now we're going to go in here. This is in OSFMK kern task. OSFMK kern task.h. I really want to see if there's any more there. Okay. Okay, now I'm going to look for struct task, a lock, a reference count, things that look for if we're in development kernel or debug kernel. This is something to watch out for. If you're trying to land an exploit against the debug kernel, your structs may be different. And so you have to, keep that in mind as you're doing this. Active, IPC active, halting, message app suspend, timers, the unique ID for the task, the map of the address space. So VM map is a structure that defines how, like the virtual memory layout of the task, a link to the global list of tasks. What's a watch port? That's interesting. Scheduling group. Threads. So this is great. So we can already see here that there's so each task has one or more threads. I think at least one. That's good. The thread count, the number of active threads, priority, importance. Okay, I thought for sure we'd be able to get this soon. So here we can actually see some of the, sorry, I'm going to make this, but these are IPC ports. So this is like the internal kernel's data structure to various ports that are for different things of the self. We'll see this in a second. The host port, bootstrap. Remember we talked about like having a send write to the bootstrap port is incredibly important because everything needs to be able to talk to the bootstrap port. And IPC space, interesting. Where is, oh, this is really weird. Just a macro in here. That probably defines a whole other data structure maybe. Data on things, BSD, there we go. Wait, if defined Mach BSD, what does that mean? Well, I assume that this is our pointer, BSD info, because it's a struct proc star, so this would make sense. Now, is there a struct proc read only? I'm curious now. Maybe that's somewhere else. But okay. So yeah, so I think I believe this BSD info is the pointer to our struct. I mean, this is the only thing that makes sense. This is the same thing. And this is, yeah, so it's defining these that will then get filled in later. Okay, that makes sense. Cool. Okay, so we have that, and then we can even go further and look at the threads. So we looked at our task has pointers to threads, so let's look at those threads. Interesting. Okay. Yeah. So if you saw that here, so we actually have a read-only thread. So a thread that, like a struct that they allocate in read-only zone. This may again be another safety mechanism if they have kernel memory that's read-only. That prevents other like exploit from writing to it. I'm sure there's so much other stuff you could write to that why you'd need to do this, I don't quite know, but you know, I guess you build up this stuff over time. Okay. And this has a pointer to its thread owner. Yeah, and so we have here, I have absolutely no idea how to understand this. Ensure nothing uses the address of thread as a queue entry. So queue entry is what we're talking about of like the data structures that you can use a struct and define like data structures on it. Maybe they did a big refactor and they were worried that they originally had a queue structure in the threads, but then eventually moved that. Like we saw, the queue structure is actually outside of this in the task struct, right? So I don't know. I can't quite see how this is useful, but like it probably is. Otherwise they wouldn't do this. But I mean, this is a big number that is not probably a pointer that's allocated, so it probably causes a failure, so they would see if it gets dereferenced. Now, the question is, wait, but this is only with, okay, if Mach assert, so you'd have to look, this is where I think the tricky thing about reading just source code is that you see things like this, that's some configuration thing, and you don't quite know if the real kernel is built like this or not. You could see where threads are allocated and then see if this magic value appears, or you could maybe grep through or search through an IDA for that specific magic value to see if that's somewhere. That could be a way to look for this because it is unique. Yeah, interesting. Okay, so this is the okay, so this is the queue chain. Okay, I guess I don't. We shouldn't get too stuck in here, but I'm just really curious. I guess they want people to access not the address of thread, but the, let's say, the run queue links or wait links or mpsec. Basically, like, if people are assuming that the thread always starts with this entry, then they could do the address of thread as they started that queue and then iterate through the queue. But this is a way of, I guess, testing that the thing should blow up if anybody does that. That's interesting. Okay.
Oh, maybe because it's a union, right? Instead of accessing. Like,
so because they'd be like, it's more of a pain to do that, so they would just do the address of thread.
Yeah.
Yeah, that's interesting. Yeah, that definitely could be. Because, yeah, the union is a pain because you have to specify which of these four you actually want, even though it's technically the same thing. So you could easily see somebody being super lazy and being like, well, I don't know which of these I want, but I know it's right there, so I just want to, I'll just use the address of that thread struct. Yeah, that's interesting. I mean, what's cool is you can see that this clearly bit somebody like at some point and they got super pissed and they like developed a way to test it. I would probably imagine that they probably internally one of their test cases enables this flag and runs all of their tests with this flag enabled to make sure that it doesn't crash or anything. That's probably how I would do it. Then your test matrix is getting huge, so I don't know. Yeah. Well, it's interesting. I mean, this is part of the thing of doing this is really great because you get to learn about. You're kind of like a software archaeologist in a way. You're like you see what's left in this code, and so you're trying to reverse engineer kind of why it was there in the first place, or what would have caused somebody to have done code like this, which in real stuff I think is super interesting. Okay, yeah, we're just scrolling through here to see which clustering queue. That's interesting. Ooh, a clutch scheduler. I don't know what a clutch scheduler is. I guess there's a lot of stuff in here. Oh, this is also something that's super weird that I've actually seen a lot in the source. They like do pound defines inside of structs. So it's kind of nice because it's like inline documentation. So you have these options and you can pretty much see that like these are the options, right? They come right after. They also start with th, probably thread and option. So you can see all the options right here in the struct itself rather than those pound defines, which seems to me much nicer style of being like not in a struct because it's not an element of a struct. It's a how to use those things. I mean, even better would be an enum, which you can actually like interrogate, but this is old code, so this probably comes from way far back. Cool. This is something we hadn't talked about it yet, but we talked about the kernel development kit that you can download from Apple for each of the kernel versions that has the release kernel, the development kernel, and the KSAN kernel. So this is, so you'll see in some of the code here something like this that actually has so if you're not familiar, ASAN is the address sanitizer that is compiled into user space applications. Is that right? At compile time, by default ASAN, right? I mean, I know you can inject afterwards. No, has nobody used ASAN? I just yes, it's compile time instrumentation. Yes, so ASAN gets compiled into your binary. So that way it does things like track mallocs and free. So if you try to free something twice, it will blow up. Or if you try to, it even looks at tries to identify writing out of bounds of the heap or the stack and all kinds of stuff. It's a massive slowdown, which is why you don't ship with this. And so KSAN, the K stands for kernel. So it's kernel, basically address sanitizer that does something very similar. So I don't know if I've ever gotten, when I was doing this stuff, I used an old Intel Mac that it was really easy to install the kernels, that I was able to install the KSAN kernel, and then I'd generate my POC and then launch the POC on that machine to get the KSAN report. And that's what I would include in my write-up to Apple to be like, look, I ran it, and here's the KSAN report, in addition with all the other stuff. But anyways, the cool thing here is that you can see that they actually have to add additional stuff to the OS to support KSAN. It doesn't just happen for free, right? Especially modifying a core struct like a thread. Anyways, other thread states we can see here. This is a really big. I thought for sure I didn't think this would be as big. Priority. Wow. Real-time parameters. I guess this supports. Seems kind of surprising-ish, but okay. And then, are we at the end? No. Yeah. So quantum history debug. What does that even mean? That doesn't make any sense. Wow, lots of pound defines on this structure. The other thing I found is that oftentimes these pound defines, these config things, usually aren't tested all the time. So you can disable something because you want to disable that feature, and then the kernel won't compile because other parts of the code aren't properly pound defined on that feature that use it. And so, it's the classic thing of the configurations that you actually run and test on are the only things that are guaranteed to work. Other things just may or may not work. Okay, I guess we're done here. Anyways, there's a lot of stuff I think we can agree in this thread struct. And a pointer back to the task that the thread belongs to. See, we got there eventually, or we got to our timer. And let's see. The other thing is this. Is this a micro thread? Is that or a U thread? It's a user thread.
It's an unsigned thread.
I don't think that's what it is, but it's in user.h. So yeah, I don't know if you noticed, but I don't prep the reading of the code part. This is all fresh for all of us. I think that's much more fun. So the book said that there was a U thread in here for BSD side of the space. So I said, cool, let's look at that. So we have a U thread struct, and I bet, let's see, we have this U thread, and I bet if we looked at proc internal, yeah. So there is inside of this is the struct, the proc struct. Inside of here, there is a list of the user threads that are in that process struct in BSD land. Interesting. Arguments to current system call, syscall code. This is weird. Anyways, user for pthread search. Oh God. Okay, so this is
according to Dr. Joe's AI, which has this works.
Is it you?
Who's to say? But says that it's a user thread, is a per thread structure XNU kernel that holds information related to a thread's execution, including syscall parameters, results, and exception handling. Contains flags that indicate the thread state, such as whether it's marked for cancellation or alternate status signals.
process? I mean, can a process have more than one of these U threads? I guess what? Because you can have. I guess, I don't know. Is this how threading works in normal Linux? No. That's like a user space thing, right? Threading in Linux? I can't remember, like P threads. Say again? I'm trying to think if it's not a, never mind. I think I'm confusing things, but okay.
Does each user space thread have its own kernel thread? Kernel thread or like a sticky thing? Is it a one-to-one method? There's a kernel thread there, like with kernel tasks and user threads are just like process threads. It'll run the kernel and you switch to the kernel itself. So it's like a kernel thread.
Yeah, they're like, I don't know, they're. Maybe this is, I guess I don't know quite where this is like used. It's also an insane, I mean, this is why you think you know C and then you see like a giant definition here of a union of structs, the different types of things. Like this is where things get like really hairy to kind of tear apart, especially just looking at the source code like this. It could get pretty complicated. You have more to add? Will?
No, I got nothing.
Cool.
Useless.
No. Your information from DuckDuckGo is very helpful. But it's like across system calls. So is this like, is this thread created on a system call, or does it handle these requests, or does it like? Because
saving the context.
Yeah, but I don't know. Does it need to do that? But it's also associated with a task. So like, I don't know. It's like, so when a syscall comes in, it knows the process that did it, and so it finds the user thread for that, but there was queues of them. Are they queued up to handle the things? Yeah, I don't know. These are all great questions that we could answer by reading the source code, which we will not do today because this is outside of the bounds of what I want to do. But we could figure it out. Anyways, ends. Okay, so the whole reason why I bring this up is let's look up task for PID, or which I think is a good one. Yeah, task for PID. So these are functions that do as the name describes.
I have a link that has a diagram that I can't see very well on my phone, but it's from Apple, so it must be good. That's an ASCII diagram.
Okay. So there are ways that if you have a task port or a port, you can ask for the process ID that is associated with that. And similarly, if you ask for the process ID, if you are a privileged user or have the same user ID, then you should be able to get the thing here. So this is a task for a process ID. So I give it a process. Wait, no, do I want the other way? I want, yeah, PID for task is what we want. This is, so find the BSD process ID of the Mach task associated with the given Mach port name. Parameters, args, user argument descriptor, indirect parameters, the port, the name, process ID. I think this will be really good because we'll walk through this and I want you to think about if and when this would be, well, how and why this could be useful for exploitation as part of a thing. So we as a user, we control the port name and it returns to us a returned process ID. So looking at the args, we get back a port name T, we get back the address of the PID. Wow, this is like deranged. Are these like tabs? No, this is like absurd. What is going on here?
Space, a diagonal space. They said to make sure it was diagonal.
I don't understand. It's so nice. These are tabs here. These are tabbed.
No, it's ordered from bottom in terms of.
This is like insane Yan style ordering of like imports by largest to smallest.
It's except for the current return key, that guy's just chilling.
Okay. Good thing we have syntax highlighting. This is a clear example of why syntax highlighting at least is nice. Okay, so port name to task name. So this is a function that takes in a port name and gives us T1. Wow. So we're writing a functions with T and T1 that are completely different types. Okay.
So where's the syntax highlighting?
Wow. Wow. I'm not in my normal thing, and also you don't need that because you can read T1 equals. But anyways, and this the coloring is different. It colors different things, and not the way that I normally think about them. So anyways, okay, so T1. So T1 is our task struct, or a pointer, probably a pointer to our task struct. I still don't know for a fact that every time there's an underscore T at the end here, it's a pointer, like a type def to a pointer of that struct. I think so, but I'm not 1,000% certain. Because it doesn't make sense, because kern return T is not, it's just the underscore T I think is type, but every struct, I think, you very rarely see like struct proc pointer. I think it's always like type defined as the thing that you would actually use. So anyways, okay, so port name to task name. So I don't think we need to dig into this. We can assume this takes in a port name and returns a task object, or a pointer to a task struct. And then if this was null, then there was a failure and go to the out. Otherwise, get BSD task info. So for T1, our task, look up and get the proc. So get the process that's associated with that task. We actually looked at those structs, right? So we don't really, this function is probably complicated because it has to do the port name, the task name to port name mapping, or sorry, the port name to task mapping. But this get BSD task info should be very simple, right? This should just look up in T1 and give us a pointer to the proc P, and then if P, so if it returns something, so this must return null, it looks up in that struct. I bet this proc PID is just a very simple struct dereference and lookup to look up the offset there, return it as the PID, and then set the error as current success. I didn't think it'd come up, but a corpse task, which sounds really weird, is a task that is dead, but the resources have been freed. So it's not using any ports, it's not using any file descriptors, all the associated resources have been freed, but the process, I guess in this case it's a Mach thing, so the task is still there, it exists, but it's not actually running. We'll talk about why in a second, or not in a second, but why that's used. In which case, it gets the PID from the task. That's interesting. Oh, maybe in this case, there is no proc associated with that. So it looks up the task PID from here, which is interesting of like, why not do that here in the first place? Why get the process? And why not do that every time? And then, task deallocate. So is this like, this is weird. Is T1 being allocated? Okay, interesting. Always something to check. We're looking at a very tiny function. You can clearly try to see if there's any use after freeze or anything like this, or unfreed memory, right? So you look at like, okay, if this is the allocation point, and if it's null, then go to PF out, which is here. Okay, that's not, and then I'd look, is there any other, like in this control flow, is there any other way to like jump right here without deallocating it? In which case there'd be memory allocated. Anyways, it's just something you can easily, maybe not easily, but you can think about and reason about a small function like this. Copy out. So copy out to the address of PID. Yeah, so we get PID, copy out to the user space the size of an int, and then exit. Okay. So very simple function. Very simple. Why might this be useful for exploitation? Let's look actually at what this does. I'm curious now because it is doing the allocation. To me, that's very weird. Okay. Port name to task name. Convert from a port name to a task reference. A name of Mach port null is valid for the null task. So here's the name. Name null, current task. If port name is pinned, okay, this is not being super helpful. No idea what that is. If Mach port valid, if the name is valid, if it's a valid name, then check if it's alive. Convert port to task with flavor locked. Just like I thought it would be.
Yeah, here it would not be happening.
You locking flavor town?
Locking flavor.
Internal helper routine to convert from a locked port to a task. Okay, so one of the, wait, no, that's no ref. Internal helper routine to convert from a locked port to a task. Convert. Okay. Task port, valid for flavor. I have no idea what these flavors are. IPC, get locked. A to do, always super cool. Oh. I mean, this means that this definitely doesn't work, right? If this, I guess this and this option is set. Okay. Maybe that's just something they don't support. Return task. Okay, I still thought this would be super easy. Look at that guess. Returns the k-object pointer of a specified port for an expected type. Okay, if IP active and type is equal to this, k-object, IPC, k-object, get raw. Okay, this isn't being as useful as I thought it would be. So we're pretty deep. Okay, well now I have to look at what this task deallocate does because this seems... Documents. Tasks in XNU are reference counted. When a task is created, it starts with two references, one for the caller, one for the task itself. If the lifetime of the task, this reference count is modified. For example, when a thread is created, it increments the reference count, and when it exits, that count drops. When a reference count reaches 0, the task is freed. Awesome. So this is another classic source of bugs. So this is another thing I should have remembered, which is slightly coming back to me as I'm reading this. That deallocation almost never happens in the kernel explicitly because objects, you take reference it, like this is insane, this reference and deallocate, because deallocate to me does not mean derect, like there's no longer a reference to it, but essentially that's what it means, right? So it's saying like if you have another reference to that object, you need to call task reference, and then if there's another, when you're done with that, you need to call deallocate. What happens under the hood is, and we can look at these, this actually may be interesting to look at, it keeps count, and when it gets to 0 in the deallocate, that's when it triggers the actually deallocates that object and it goes back and frees memory. But if there's ever any mismatches, right? If you have one path where you're either deallocating something, but there's still a pointer to it, and you deallocate everything else, then boom, those things, the object gets freed, and you still have a pointer to it that you can try to reference other objects. That's a use after free. Similar things happen if you do it the other way around. Basically, if you can mess with this reference counter, then you have, you're going to have a good time, although it can be a pain in the butt. And where were we going? Oh, it may not be. It might be a macro, which is why I wasn't able to easily find it. Let's see, if I was a macro, I'd probably be in like task.h, which we're already in. Now I need to look at the grep. There we go. So I just looked for pound define since I was already in there. There we go. Task deallocate task deallocate group, and then passing this kernel thing. If this was task ref.h, is there a task ref.c, which there is, which would be where reference counting is done for tasks. Assert 3u, this is weird. Clearly this must be a macro because I don't think you can just pass a less than symbol to a function. That doesn't make sense. We'll see your syntax highlighting deal with this. And you'd have to check, I can't remember if assert statements always get compiled in or if they only get compiled in on development kernels, or if it depends on what the type of the assert is. I think they may always get compiled. Which actually, these are great sources of mapping the kernel source code to the binary code, because oftentimes the assert statement will include the line and the exact file and line number where the assert failure happens. So you can, when you don't necessarily, like if this got compiled or inlined into some other function, you can more easily map the source code to the binary code that you're looking at in IDA by looking up these functions. There's probably a better way to do it. I think somebody should just write a freaking IDA script to just like do this, but like, I don't know, IDA scripting is painful, but okay, let's look at this. So we are, if the null task do nothing, so don't deallocate a null task. Okay, if we're deallocating a group, we're allocating a group. OS ref release lower. Okay, so it's this ref count in the task. So task ref count.ref count. And this thing, as we can see, is actually could deallocate the task itself. And then it calls this internal thing. What? It's setting the counts? Ooh. But I think this one should set the counts. Like reference release should yeah, I think because this can free the task. But let's we were just, I think task.c had this. Yeah. Drop a reference on a task, don't call this directly. I love when you just have functions like don't call me. Ledger amount, okay, weird. If the task is null. Oh, the number of references. Okay, if the number of references is 1. If the references is greater than 0. Okay, so this actually deals with that. Yeah, so this is the thing that checks. So if it has 0 or if it's greater than 0. So at this point, the task should be dead. Ensure the resources like threads are gone before we trash the world. So a bunch of asserts saying that like the queue is empty, the task BSD info. Sorry. The other thing that assert statements that I just remembered that can be very helpful is like figuring out, so you have this assert not task active. So I think the text of this, not task active, actually gets compiled into the kernel. We had a kernel open, right, at some point? I don't know why I'm just talking about this when I can show you it. It's the new OS. It has a whole bunch of crazy stuff. Can you all read this? Okay, let's see if this was task deallocate internal. And this was some release kernel. I don't even remember exactly what version this is or what I was doing on here, but okay, well, I don't think those asserts got compiled in, but this one did. Wait, is this?
C line 2147.
Yeah, but I don't know if this was this exact version, so let's look for this string. The problem is this won't be on an assert statement. Yeah, this is like an official panic. Anyways, why I was going to say that is, okay, we can see that there's an assert here, so yeah. So this is not happening in that kernel, the release kernel, which can be very nice for exploitation because then you don't have to worry about those asserts. I thought I did. I may have a debug kernel. Since we're doing this, let's okay, so this was, oh yeah. And let's check over here. This was in temp kernel release. Say that again? Yeah, that's what I want, this development version. Oh, you saw it somewhere else? Well, too slow. I can't remember which one to open for this when it's like this. Oh, this one? Yeah. I don't know if this is exactly the same version, but it's okay. I think we're close enough, so. Yes, import everything. This is going to take a while. Okay, we'll come back to this. We'll pop back up and then we'll look at it again. But even things like this, the panics can be super useful. So when you're in here, you would know, if you didn't know the task struct or, I guess, why doesn't it know that this is like a task T pointer? Not sure why it's doing this, but you could easily see, okay, task plus 355 is task volatile objects. Task plus 356, although this is what, treating it as a unsigned int pointer. Anyways, you could map. My point was, if you have the asserts, it can also be easy to map variables to where they're used because they're oftentimes as part of the assert statements. Otherwise, if you have panics, you can see the files, and also this can help you to map the variable names.
It shouldn't be a pointer, I think.
It shouldn't. You think this is a raw task struct?
Instantly dereferencing it. It's adding the offset to the base thing.
Well, that made it worse.
Oh, sometimes you just gotta try.
Yeah. You called it a task T. It's calling it a task T underscore 0. So item may have pulled multiple from like the debug symbols. Multiple?
Oh, maybe it has an individual one for like each union.
Great.
Yeah.
Don't even want to think about that. That sounds horrible. What a world to live in. Okay. So we can at least maybe try. Yeah, there we go. So now we got the asserts. Okay. So we can see, so this was the debug, or the development kernel. So we can see the asserts in here. So anyways, those can be helpful. You can also, yeah, particularly with, because the thing that's a problem when doing this is functions that are static. Did I already talk about this? So a static function is only accessible in the file that it's in. And so by default, those do not have symbols. So like, because they don't need to be exported, the compiler just doesn't include them. And so if you have some of these things do have a lot of functions. So even when you have development with symbols, you can have just functions with no names. Similar thing can happen with inlined functions. So functions that are inlined. I wonder, did it hit any? It must have been this one, right? Yeah. So here's like functions. Well, maybe not functions. Yeah, this is definitely a function that does probably something. And this is probably a, how do I filter? Oh, Control F. Yeah. So you can see here there's a bunch of functions that don't have any names. And if we wanted to know them, we'd have to do this. Oh, what I was talking about. I guess there's way less in the development kernel, which is nice. Ida, you're making me look bad. They're not going to believe anything I say. Oh, something has to be a function. Is there a way to show size in here and everything? Anyways, I don't care. Why am I doing this? Okay, pop back up. Asserts can be useful. Point of this diversion. We were looking at deallocate internal. Okay, so we got to here, and this is, it should probably strike you, one of the things always that I think about when reading code is like, this code looks complex. It's doing a lot of things. Does it need to do this? Like, is it needlessly complex? In which case, like, great, like complex code is always a good source for bugs. When I look at this, I think like, is this the way I would have done it? Right? So like, okay, your reference counter is at 0. You definitely want all these asserts to make sure like the object is actually empty and everything that was before you that was supposed to deallocate those things does. And then you're going to do things which are then going to set other reference counters down, which then may deallocate objects. This task IO stats gets explicitly freed. We haven't gone into the different like allocation things, but we can just think of K free. I think there's different types of K free, and data is like one type of thing that it allocates and deallocates from. Give the machine dependent code a chance to perform cleanup before ripping apart the task. Cool. So call this machine task terminate, and then IPC task terminate, and then this IO kit thing. Disown all the virtual memory objects. Assert that this actually happened, right? That's a good practice. Panic if we still own objects, because that's going to be very bad. So you can see the other thing, the programmers, at least at some point, were thinking about the differences between panics and asserts, right? Because asserts will only happen on the development kernel, but panics get built into the system. Deallocate the virtual memory map. I want to read this as is release, but this doesn't make sense because is release to me should return a Boolean that you check. And so IS must be something else that I don't know what it is, and it's releasing that probably. But this maybe ITK space, some ledger stuff. These ledgers are weird. accumulate stats for dead tasks. And then freeing a bunch of, or freeing other counters that it has. And then finally destroying it. Yeah, there we go. This is at the very end. Z-free is another type of kernel free that you specify this. I think it does a check of making sure that what you're freeing from is in that zone. I think that's what this is for. So you need to make sure the allocation is on the same side. Okay, wow. I've lost track of them. I remember the entry point where we started and then right here, but I cannot remember in the middle of where we were trying to go. Task structures.
Task structures. We were talking about it. It was the task port name thing, mapping.
We looked at.
That's where we came from.
Oh, task deallocate. Okay. Yeah, PID for task. Okay. Whew. Cool. Okay. So we were talking about how this could be useful for exploitation. So I didn't tell you what primitive you had, so it's kind of silly because you can think of the entire world of things that you could have done to the system. But let's say you were able to get a task name that pointed to a fake task that you created. So you were able to like do a use after free on the task and like your data gets put there. So you have a pointer. Now this name points to a task, the port name, yeah, I think that's how it went. The port name points to now a task that you control. So what happens next? Yeah, that's not right.
I mean, like you could allocate a task structure, and it's like you create the representation of a task in memory.
Sick. Let's go to the source. Okay. Yeah, okay. So the idea is that by creating a fake task port, we can use that to read arbitrary kernel memory by asking for the PID, because essentially it does like just several dereferences, right? So it takes the task, it gets the task port. Using that task port, it does a dereference, and then there it does a dereference to the PID offset and returns it to us as an integer. So this, yeah, you have to have a whole other vulnerability. This is like we are halfway through a giant blog post about how to get there. But this is why it's interesting, because even though it's like not a getting there is hard, but that's not the end of the story. You still need to be able to do things like turning a use after free into reading and writing memory, right? Or reading memory, which is a first step towards doing what you want to do. Let's see if they have code so we can actually look at this. Yeah, okay, so here we can look at the what this would be. This was circa, let's see. You always want to remember the dates on these things to map it to if this stuff is useful to you, because the kernel has changed in the meantime. This is by Brandon. Brandon Azad. Wait. An iOS hacker tries Android. I don't want... Oh, I guess he's theoretically talking about... this is super interesting. Anyways, I'll mention Brandon has really awesome stuff on iOS. So, okay, this is actually a great, because it's not a, not actually, this is even just like a fake iOS heap overflow. Okay, well, we're just going to read this together as a group, and that I will read it to you. Imagine a heap overflow bug existed on iOS. Imagine there were a race, whatever, don't care about that. We have a linear controlled heap buffer overflow out of a controlled size allocation. How to turn this into an arbitrary kernel read-write. On iOS, the final kernel read-write capability has been to use an object called a kernel task port, right? Which is what we've been talking about. A task port is a handle that gives us control of the virtual memory of a task, and a kernel task port is a task port for the kernel itself. So we haven't got to the task port yet, but one of the cool things about task ports is they let you, literally, there's a message you can tell the kernel to read and write memory of that task, and it will just do it. And one of the tasks that you can get is the kernel task port that allows you to do this. So it's really cool. Oh, yeah, literally. Okay, this was the other parts of my lecture, but we're getting there early. If you construct a kernel task port, you can use standard APIs like Mach VM read and Mach VM write. So these are technically like that MIG interface things. They're not system calls again, right? These are messages you're sending over a port that you have got that you're telling the operating system, I want to do this, to read and write kernel memory from user space. Possibly. I don't know Windows enough to say that. So yes, you tell me. Okay, so let's blah, 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 blah. The most straightforward way to get a handle to a task port using this primitive would likely be to overflow into an out-of-line mock ports array and insert a pointer to a fake kernel task port such that receiving the overflowed port array back in user space grants us a handle to our fake port. This is basically saying like, yeah, so, okay, but let's get this and then say, unfortunately, the first time we trigger this vulnerability gives us a handle to a fake task port. We won't have all the information necessary. We need to leak the addresses of a few important kernel objects. Yeah, so the idea is you get this, you do this overflow. So this is actually why we've been talking about like mock ports and stuff, because this was a big strategy for exploitation. So we can send ports, right, in our messages, and you can send an like arbitrary number of ports. And so the idea is by sending them out of line, the kernel like copies them. And so if you can get that copy after your overflow, you can overflow control those ports and then receive that message back from the kernel. And now those ports have been changed from what they should have been to, your goal is to get a fake kernel task port, but you need to know certain memory addresses in order to create that. So first you create one that is not a special task port, but that you can use PID for task on it. And by reading the kernel memory, you can go from there. Anyways, yeah, this is like all kinds of exploits that like exploitation techniques. I think we'll get, my goal with this class is I want us to get here to be able to actually do some of this stuff, maybe on older kernels. There's also newer exploits that work against our current kernel, which are very cool. There's like a physical page use after free, like where the physical page isn't freed, but it's still in use, and you can allocate other stuff over there. I think that'll be one of the first ones we do because it'll be very easy because I think the infrastructure is kind of set up for that. So anyways, this is why we're talking about all this stuff, but you can see like the craziness that has to happen for these types of exploits. Cool, okay. Anyways, PID for tasks, great. This is a standard technique that's used by exploiters. Whew, that's what all this was for. All right. Okay, cool. That's why we talked about tasks and processes, because something super simple like this actually leads to a very critical exploitation primitive. Now, getting to task ports. Task ports, these basically allow you to control a specific task. The function mock task self is what returns the write, the send write to that port. So every process has their, or sorry, no, we're not talking about processes. Every task has its own task port that the kernel has the receive end of, and the task itself has the send write. Does that make sense? And this happens, I believe, on task creation. Yeah, it's how it works. I don't know. Like the need is interesting question. It's more of like a it is, right? It goes all the because it goes really all the way back. I don't know what that means. It goes all the way back to like the Mach kernel itself, because this is how you would do things like ask the kernel like to terminate you. I mean, this is one of the things that you can do to like task terminate is something you could do to like stop running. There's also like task suspend. You can suspend yourself. You can give if you wanted to, you can give another task the ability to suspend you, which is how you could do this, right? If you're developing like, you know, a thing where like one task is forking and then executing other tasks, they can like, but you want them to be able to control them, you could send them the task ports back so that they have the ability to do this, basically like delegating responsibility or control over your task to other tasks, which is kind of cool. I mean, that's what this stuff all allows. I think it came from the sense of just like this, it's like the anybody familiar with or the concept of Plan 9, the operating system? So Plan 9 was this was it a Bell Labs thing that was going to be like a reimagining of Unix where like everything is a file, was like Plan 9's like central thesis. Like you want to talk to the network, you talk to a file. You want to configure, like this is where I think the idea of the proc file system and these things kind of came from, because Plan 9 was like, how can we take this all the way to the edge and just be like crazy? Where literally everything in the operating system is a file. You can see it didn't like catch on, but I think that's a kind of thing where like the Mach thing was like, what if everything was a task and they just talked with this Mach IPC with these ports? And that's it. The crazy thing, I think I mentioned this a little bit, but the book mentions a little bit that the original design of Mach actually allowed you to run different tasks on different machines and it'd be purely transparent. So if you could send a message just like you guys are sending IPC messages, and then the operating system would say, oh, that's on the other node, proxy that over there, get the response, and then send it back, you know, to your thing, or not send it back and not have to send it back. So it's a very flexible mechanism that allowed for this microkernel design. And then I think they were just like, you have a problem to solve, you like use ports. Like that's how you solve that problem. Creating new threads. So this would be something that a task would want to do. And yeah, so this is like also manipulation of a task. So basically, if you have the send write to a task, you can do like almost anything to it. Let's go look at some of the other things in here in mock task H because they're super interesting. No, this is mock task. No, that's not right. Yeah, there we go. Is that right? Yeah, mock. Because these are all user space stuff, so that's why we want to look at them in here. So these allow you to do things like task create, or I guess this would be a thing to create a task, terminate a task, get the threads. I think this will maybe either send you information about the threads or it may send you the thread ports so that you could then interact with those threads. Let's see, what are some interesting things? Task info, not interesting things. Set info, suspend, resume. There are task special ports, not a ton, we'll talk about them in a second. Creating new threads, create a running thread. Exception ports again, boom, pop up again. I mentioned they would. Swapping exception ports. I don't know what a lock set is, but you can create them and destroy them. Oh, this is interesting. Creating semaphores or destroying semaphores. Policy, sample, emulation. I don't know what this is. Assign. Doesn't make sense. Wait, should I have seen how big this file is? Oh, we're only 15% of the way there. Okay. Wow, this was a mistake. Oh, look at this. You can just look at this. We don't have to scroll through. Excuse me. The voucher thing, that's fine. Let's see, inspect. anyways, I guess not that interesting stuff, except for the next thing. So these are the task ports. A task port also allows a virtual memory access and modifications. That's what we just saw. So in Mach VM, there are things Mach VM write and Mach VM read, which allow you, if you have the task, to be able to we actually just saw this in Brandon's post, where I want to actually go to the files. It's Mach VM. So like write is the task, an address, data, and how much data. So just literally, what? Oh, weird. Get better. Okay. Can you read it now? So all you need is the task, the address, data, and the amount of data, and you can write data there. Like, it's crazy. You can read Mach VM read. You can read any data from that task. So with these capabilities, you can inject new threads. You can inject new memory. You can read and write and change memory, right? And I believe, do tasks share a virtual memory space? Or do threads in a task share a virtual memory space? I'm going to say yes. That's the thing that makes sense to me. So we can look that up, but it would make sense. That's the similar concept, thread concept in Linux, right? Like,
mappings are like the actual. Do you share your virtual address mappings or the actual?
Yeah, the VM mappings. Yeah, so you could from one thread. So you could literally inject a thread into a task that could run in the same address space and do whatever it wants. It can load a library. You can inject a thread into a task and load a library, and that library is now just running in that as part of that task. You can pause the thread that's currently running. You can then inspect the memory and then just change the memory of that process. There are some restrictions, I think. The operating system still does implement some memory protection, so you can't go absolutely crazy, especially on the kernel. But this is very, very powerful primitive. You can do anything to this task that you want. Say it again. Yeah, this I think is also exactly from the microkernel design. So and this is how debuggers work, I believe. So under the hood, they get the task port for the task that they're debugging, and they can do things like suspend it, resume it, modify memory, read and write to things, do all of that through these things. So then you don't need special debugging capabilities because the kernel gives it to you, right? And as long as a task gives you that port, then you can do, or the OS does because you're root, then you can have total control over that task. Cool. And as we mentioned, and Brandon spoiled, kernel task is a special task port that represents the kernel. This means that if you obtain a send write to it by either getting it, tricking it, or creating a fake task struct that does this, then you can read and write kernel memory using these primitives. Now there are some SIP and other security mechanisms. You don't have I think directly modifying, because I can't remember if through this you can change the kernel memory mapping of the protections of the memory pages. So you can't just modify kernel code directly, because then that would be you're still not, they're still implementing what is it? I want to say NoX, or NX, or writable or executable, right? Memory can't be both writable and executable. So the kernel, either the hardware supports that or the kernel supports that on these things. So, but this is, as we saw on that blog post, this is the end. This is pretty end game. You get this and you're in a good state. Great question. Should we look at it? Let's look at for write. So let's look at the code. I mean, it won't be able to tell us right away that it like, yes, it's very fast or very slow, but at least we'll be able to see, is it very complicated or is it literally just like copy out and like do that? It may have to look up the memory mappings. Here we go. Okay, overwrite the specified address range with the data provided from the current map. So check, okay, VM map copy overwrite, map address, data size, okay, false, so this is just a wrapper. The code you're looking for is in another file. vmmap.c. So we're actually pretty, let's see, where are we? In OSFMK VM. Yeah, like I mentioned, like the Mach side of the kernel has a lot of the real capabilities, like the virtual memory mapping, this kind of stuff. So let's read the documentation, of course. Wow, okay. Copy the memory described by the map copy onto the destination region. The destination must be writable. Unlike VM map copy out, this routine actually writes over previously mapped memory. If the previous mapping was a permanent memory object, it is preserved. The attributes, protection, and inheritance of the region, destination region are preserved. If successful, consumes the copy object. Otherwise, the caller is responsible for it. That's weird, but okay. Implementation notes. To overwrite aligned temporary virtual memory, it is sufficient to remove the previous mapping and insert the new copy. It also trips me up. I don't know if you all noticed this, but there's 2 spaces here after the period. This is like bonkers, but anyways. This replacement is done either on the whole region, if no permanent virtual memory objects are embedded in the destination region, or in individual map entries. To overwrite permanent virtual memory, it is necessary to copy each page, as the external memory management interface currently does not provide any optimizations. Unaligned memory also has to be copied. It is possible to use VM trickery to copy the aligned data. That seems very sketchy. You should look at whatever the hell this is talking about and see. Virtual memory trickery should not be a thing. This is not done, but hard. Wait. Oh, okay, good. This is not done, but hard to implement. Okay, great. This is, but maybe that's a lie. This code comments don't execute, so this could be full of crap, and that actually is implemented, and it is tricky, and it was incorrect. Once a page of permanent memory has been overwritten, it is impossible to interrupt this function. Otherwise, the call would be neither atomic nor location independent. The kernel state portion of a user thread must be interruptible. Here's at least a question. It may be expensive to forward all requests that might overwrite permanent memory to uninterruptible kernel threads. This routine may be called by interruptible threads. However, success is not guaranteed. If the request cannot be performed atomically and interruptibly, an error indication is returned. So this is saying that like it needs to do these things in a kernel. Is it calling it a kernel thread? Yeah, in a kernel thread that's not interrupted. So that would probably be a kernel thread that lives in kernel task, that kernel task that we talked about with the ports. Callers of this function must call VM map copy require on previously created VM map copy T or pass a newly created one to ensure that it hasn't been forged. Okay. Wait, why are we in nested? Did we go too deep? Oh, where's the... Okay. Let's look up... Wait. We were looking at write, right? Were we looking at read?
Right.
Yeah, okay. I was like, why? Okay, VM map copy overwrite. We're passing in a map, an address, the data, the size, and if it's interruptible, and interruptible is false. So Okay, head size, tail size, head copy, tail copy, head address. Check for null copy object. Assert that the VM map copy is coming from the right zone and hasn't been forged. So this is a clear protection mechanism that somebody had to create at some point. If it's interruptible, which we know is false, or the copy type is not a... we can't split the copy map if we're interruptible. We don't have a copy map. Blunt copy. That's weird. Okay. I don't know. Does anybody see? Is this efficient? We'd have to get pretty deep to understand that.
It sounded like they were actually creating the whole mapping for this page, which doesn't really sound like it's efficient.
But it seems like the logic is too small to bother with optimizing.
There is the other nested function.
Yeah, that is.
VM map copy override optimization threshold pages. So if the size is less than, I guess this is saying probably, okay, let's see. What's this? Desmap, desser, copy, interruptible, null, true. This is weird. Because we were looking at this. Oh, discard on success. But this, where's my blunt copy? Oh, it does pass interruptible, okay. So this is just like the, so this is probably what get called in that circumstance because it's like, I don't think we have a map, we just have like an address that we're copying from, is how I read that, but maybe not. But okay, page shifting, trying to figure out the copy size, incompatible misalignment, proper alignment or identical misalignment. That's a weird statement. Try to do a small unaligned copy first. Oh fuck, this is a lot bigger than I thought. Assert. Wow. Okay. The blunt copy should be easy, right? So I'm gonna go with, it's not super fast. I think maybe the thing here, but let's like briefly scroll through this. Well, if we're just copying a kernel buffer, then like do this. So some quick speed up thing of like checking that we're not doing something super crazy, or only works for entry lists. We'll support page lists later. VM, so the type has to be VM map copy entry list. If size is 0, then we're just done. We don't care about it. If the page shift, verify that the destination is all writable initially. We have to trunk the destination address around the copy size. Will end up splitting entries in strange ways. So if we're page aligned on the size, I wonder if there's a check on this copy size. Because this looks like it could overflow in a weird way, maybe. I guess that would only be if it's at like the end of memory and like, I don't quite know what these things like look like. Maybe this would be a good thing to, next time for the dtrace example, we can try to like log how fast this stuff is. But anyways, this is fun looking at. Okay, remove this check. Start pass 1. Okay, definitely it's not looking like it's super fast if we have multiple passes out. VM map clip start. For loop, looping over there. Yeah, I mean, this would need a lot of information about the memory matching system, which like, I don't know. Maybe we'll get there at some point, but like this is, as you can tell, a very complex beast. So Yeah, I'm gonna go ahead and say not the fastest. But from your perspective, it doesn't matter because it just works. You just call the thing and then boom, the memory changes. And so as long as that happens, you're good. Wow. Performance gains. Oh, thank God. I mean, there's no way this code does not have bugs in it. Like this is, we saw us scroll through this. This is like impossible to write bug free, I think. There was it Ian who had, zero bug. Was it this one? This one? Yeah, look, I think this is the thing I'm remembering. Like, just we'll read just this thing. A locking bug in the XNU virtual memory subsystem allowed violation of the preconditions required for the correctness of an optimized virtual memory optimization. So I think this means they weren't locking a memory page while doing stuff to it, and so they were able to modify it and trick it into doing something. This is abused to create shared memory where it wasn't expected, allowing the creation of a time of check, time of use bug where one normally wouldn't exist. I just want to see where this is. Yeah. So this is, huh? I mean, it may be. That's kind of what I was like checking. Just like my intuition is like, yeah, there's definitely something weird here. Yeah, anyways, I remember there was a good thing in here, so this would be something to look into. Okay, we've looked into this enough. I have no idea, but it seems very complicated, and for sure, anything virtual memory related that is complicated, great source of bugs. Like, especially because you can do this to your own task. You can like read and write memory to your own task. You can like launch two tasks and get a send port and send, do this to another task. So you can control a lot of the data this is using, right? And then also do things concurrently in other threads of messing with virtual memory. So you could be simultaneously doing this operation while also then changing a memory map. So maybe the memory gets moved out from under the OS when it writes it, and so it ends up writing into kernel memory. That would be like one type of exploit that I would think about here. But yeah, like for sure there. I don't know. Are there any multiplies? I guess we didn't look at the types of the variables. Also, the types can, yeah, like look this. I mean, these are ints. You look at like, can I overflow this to be a negative number? Can I make it very large? How do I control these things? Let's see. What other things would I look at? Yeah, I'm looking at the types here. Yeah, this, I mean, a 16-bit thing of, which goes right in from there, this page shift. It's then coming there. Okay, maybe it's not actually used, but anyways, that's if there's any addition operations or if that's used somewhere else, right? That's where I'd look for, or addition, multiplication, that's where I'd look for because it looks like that's something you can control. Anyways, you can look for very simple things like this. Understanding then the semantics of exactly what it's doing would probably then actually lead you to find a logical flaw or an unlocking thing which leads to a race condition. This kind of stuff. Okay. So Mach VM read and Mach VM write. Very complicated things. We talked about that. Finally, so finishing our host, task, and now threads. We're at thread ports. So thread ports allow you to control / modify threads. You can terminate them, suspend them, set exception ports, which we're going to finally get to actually at the end here. And there's actually not a ton of things you can do here, but it's definitely, there are some things. Now, an interesting thing. So I think it was all the way back in the host port, you could get the processor set ports. So these are information about the processing, like the actual like representing a CPU. So a processor like represents a CPU here. There apparently used to be functionality where you could group them together into a collection. So you could like have different tasks running on different processor groups and like configure it. But now there's just like one process group and you can't actually modify it and touch it. But there's two very special methods. Set tasks. Wait, that can't be right. Set tasks? Yeah. Oh, yeah. Sorry. I always think of it like processor and you are setting tasks, but it is processor set tasks. This returns the ports, the task ports of every process that's running, every task that's running on all the processors, which is all of them. The processor set threads returns the thread ports for every thread that's running on the system. So if you're going to exploit this, what would you do? Or is this a problem? Every task in the system, you get a task port to. Yeah, but which task do you want? Which is your golden task? The kernel task was one of the things returned here. And so you could just get easily kernel read-write access from this. There was a Black Hat Asia 2014 talk about this. You can check it out here. There's a good write-up here. So I want to check this out so we can see that, yeah. Okay, that's interesting. You used to be able to apparently just access the kernel task by, it was considered process 0, so you could just say task for PID 0. Then you could just read-write kernel memory. And you needed root, of course, to get access, but that would allow you easily root to kernel access. Oh, we're going to look at the code, but okay, we'll still look at the code, but let's see. But where is it checking? The 0? Yeah, but that's PI. That's checking. Oh, if the PID you're asking for. Yeah, process ID 0. Sorry. I was thinking your PID. That doesn't make sense. But this is an arg, so yeah. The argument PID 0 always returns a failure. That way you can't ask for it. But this is where so then the interesting thing is, one interesting thing that this had me thinking about is what other bypasses are there to get this kernel task port? Are there other things where you could ask for it? That would be very interesting to look through the code. So yeah, the processor set task lists all the tasks, and it returns the task port for all tasks, which is everything. And so you just set all the necessary ports. So you use this, call the function, you get the kernel task port, and then you can use that to use Mach VM read and write to read and write from kernel memory. Cool. And yeah, you still need root, right? Which is fine, but like we said, kind of cool. So this would definitely be something you could get paid for by Apple. Okay, so let's look at, but it is now very locked, significantly locked down. There's, we didn't talk about the entitlement systems. I don't think we're gonna get into it, but there's specific entitlements that they can check for that a process, when it's calling a system call or talking to the Mach kernel, has the entitlement to be able to do that. So let's look at processor set things. That's what I want to check next. Yeah, here we go. Common internals for processor set, threads, or tasks. So set things does both. This is the helper. like I've mentioned, you can see here the static. So let's see if I'm not full of jokes, as Jan would say. Okay. Go to this. Shit, it does exist. Why does it exist? Oh, that's handy. All right, I don't know why this name exists, but this is great. Maybe it needs it because it's, I don't know. Okay. But anyways, we could trace, I'm sure processor set threads ends up calling this, but let's look through here for the code that checks for this, that tries to redact it. I think it's technically not in here, but that's okay. We'll find it. Okay, so we have the task list, thread list, and a void star thing list. You don't like the thing list? Justin is furiously shaking his head. So, okay, we'd be doing set threads, or no, set tasks, which just calls internal. Back to Flavortown. Okay, cool. Okay, so, oh yeah, just literally, what? Wait, but this is the internal, sorry, this is internal. Yeah, okay. But, so it still just points this void star, so this task array T task list. I get, oh, because you don't know if it's tasks or, wow, that's crazy, okay. I don't like this at all, but the code must be very similar. Okay, checking pset processor is null, just return the empty argument. Task count current, blah, 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 blah. For blah, if type is equal to pset thing thread. Wow, that's really annoying. Wow, this is super dangerous. Do you guys see this? Just like a dangling else. So if not config Mac F, then it's this or this. Otherwise, it's always this. It's both of them. Yeah.
Well, if it's not config MacF, then it's either or. But if it is, there's always that one.
Yeah, that's weird.
So why write a for loop like that? Was QA just like no while truths? And so it's just...
That's a good question. I think I vaguely remember hearing some kind of story about this, but I don't know. Oh, wait, I don't want to sign in. Jesus Christ, the whole screen is pop-ups.
It's like we're back in 1990.
Were you born then? Don't answer that.
You don't want to know?
My coworker said that a professor had told them that the WoW 1 was doing a comparison 1 equals 1 and the 4 was not. You repeat the same steps. Not clear from the question, purely a fun academic discussion. Which infinite loop is fastest? That's fine. In Perl, they use the same opcodes in GCC. Okay. I mean, maybe this. If I have a loop that never ends, I prefer the 4 because it's weird and it makes people think.
It did its job.
Oh my god, what?
That's something.
That's crazy. Okay. That's what I was thinking. I don't know. That's my thought was that when did the C? But like that can't be true. There must have always been a while loop. Like you can't invent a programming language without while. Okay. Fantastic. If anybody's on chat still, I have absolutely no idea. But if anybody finds this out, oh my god, you have to do it every time because I'm in the. Yeah. So short version, absolutely no idea. Again, this is what I said. Like reading real code, you find like absolutely bizarre stuff that like you're just like, but what? Why? Like you can, but why? Because it's not for anything. It's forever. Okay. And then you have this dangling thing, super weird. Okay, so yeah, if we're doing threads, then the thread count needed becomes the thread count. Otherwise, the task counts needed becomes the task count, which gets passed in. Where are these counts? Oh, these are, oh, because it's all of them. Duh. Okay, these are global variables that are keeping track of how many threads. I was like, where do they come from? Yeah. That's interesting. Okay, let's see what, okay. This was the first thing I was looking for, some kind of lock on both of those information. So you see, this is also the problem you're talking about, like inefficiencies, right? Or like, you have to have this weird void star star, which is a red sign in the current, like you should not do this. Also, you have to have a lock that locks access to here for, you have to do this with, you're messing with either tasks or threads, right? So it'd be more efficient if you only locked the thing that you actually need access to and not the other things. Okay, anyways. Counts, if count needed is less than or equal to the task count cur. Okay. Break, unlock, and then allocate more memory. Grow the tasks array. Ooh, this is, I found a bug in something like this before. Okay, so let's pay attention. Grow the task array. If task count needed is greater than task count current, free the task list. So the task list is initially null. Assert that the number we need is greater than 0. Task count current is equal to task count needed. And then task list, KLF type. Task T is greater than task count cur. And if task list is equal to 0, or if we couldn't allocate it, then we're screwed and nothing will work anyways. The Z0 flag tells the kernel to 0 the memory on allocation. You'll see this all over the place. And I think this wait okay means like I'm okay to wait for that memory. If like you're under memory pressure and you can't give it to me right away, I'm okay to block waiting for that. So how did this get incremented? So task count current is equal to task count needed, which, okay, but where does it get incremented? Does it only ever increase? This is weird. It's like looping, trying to get all the tasks or something, and then but if there tends to be more tasks, it'll like jam them in there or something. Yeah, but usually, so in a realloc loop, you'd have something that like increases the size of the thing that you're reallocating. So you'd like, I don't know, you'd start and like every time you'd be like, let's double it and get more memory, or let's increase by a fixed amount. And that's a case where if you can get it to overflow, then you have a bug, because then you have to copy the old stuff into the new stuff, right?
Well, right up there, it breaks if it's less than.
Yeah, so it's done enough or done all, like, I think it's only just using the count of what tasks. So like these task globals are probably being like allocated, like incremented and decremented all the time, right? As more things happen. So probably just like, I don't don't know, gets the current tasks and then is like, oh shit, is there more tasks? Like, let's add more or get more. I don't know.
I mean, that lower part is just creating more memory.
Yes,
right?
yes, yes.
If you need more.
Yeah, it's allocating more memory. This part here, and then growing the thread array, same thing for the threads. Oh, so it's just allocating memory. But
yeah, if you don't have enough. Because it probably reuses the.
So like what continues doing this and like. So this, I mean, if you continually just have more tasks, this will just like keep going. Like, because it'll keep like freeing memory and then allocating memory and then there's more tasks.
Not with that wait okay. Maybe it
Which one?
pauses there, right? Like if you spawn too many threads, essentially it's gonna wait and not actually spawn the things needed to make a new one until there's enough memory.
But I mean, so you have one thing that's just creating new tasks, right? And this thing where you ask for the current tasks, and this thing would just keep going and like, well, there's 5 tasks, so I need to allocate that. But the time I get around to the next thread, there's more, so now I need to allocate 10, and the next time 20, and then 30, and then.
On that note, what if you have like a task that's entered to this list, but then it gets removed?
Yeah, that part I don't know quite yet. I think this is only allocating memory, so it's just like.
But then eventually it's going to have for these tasks.
Something. Yes, that's the part I don't know yet. We haven't seen where it's going yet, right? So okay, this is just allocating more tasks, more threads to like get the stuff. Okay. Have memory and the list locked. Do you have the list locked? I guess here. But when it breaks, it doesn't unlock it, but it unlocks it here. Okay. But then it goes around and then it locks it again, and then if it's on here, wow, this is a terrible design. Okay. Whew. Okay, so if we currently have allocated enough memory for the current task count, and we've currently allocated enough threads for the thread count, then we've locked, we still have tasks threads locked. So now we're here. If we need to get the thread list, this is so weird. You've allocated memory for both tasks and threads, but without actually knowing which one you need. But okay, so if we're getting threads, then this is weird. Who would not define a secure kernel? But okay. Q iterate. Oh, this is what I was saying. One of the functions over starting with the address of threads, thread t threads. I can't remember all the things here, but task is equal to get thread task thread. Okay. Well, this is great. So here we can already see here if defined secure kernel. Do not return the kernel task. Right? This was the exact thing that we were trying to find, and we found it. Yay. Okay. If it's in the middle of an exec, that's interesting. Reference, thread list, actual threads ++. This is so weird. Otherwise, then also do this. Oh, this is the threads, yeah. And then the task, if the task is the kernel task, then skip it. Okay, and now unlock. Okay.
I said iterate. If you go back up real quick to one more up.
Yes.
To
the thread.
It's checking the task there too, though, and not the thread. Oh, it's making sure that the thread does not belong to the task.
Yeah, exactly. So it has to do extra work to figure out the task associated with this thread, and then check and make sure that that task is not the kernel task. But we are not done yet. So the config macf. So this is a. So let's. I cannot remember what this is, but we'll look it up real quick. It should. That's what we're looking and verifying. This whole thing was just verifying that it's not vulnerable to this thing from 10 years ago. If it was, that would be super cool. No, I want specifically. Aha. Just like you all know, because you've studied security, mandatory access control is very important. And so MAC-F stands for not like Macintosh Mac, but the Mandatory Access Control Framework, which basically allows, so there are different kernel extensions that can install hooks. So the actual logic here is not in the kernel, but these MAC-F, this Mac task check exposed task has to be registered by an extension that gets loaded, that then the operating system calls into it to see if it should load these things. This way it's very extensible, and if they need to, if there's a problem, they can change things. So this is also where it's doing this. You can see that it does task deallocate task list I, so it gets rid of it. And yeah, this is exactly what I wanted to check. Yeah, for each task, make sure we're allowed to actually examine it and return it. Because there's also, like I said, SIP restricts what the root can do, so you actually don't get every task on the system. So you definitely don't get the kernel task. We saw that that is like hard-coded into the OS, that you do not get the kernel task. We also saw that you, this makes sure that like important system tasks aren't returned as well. So you can't easily circumvent their functionality by getting their tasks and then having access. Like the, we looked at the AMF. Is that the one we looked at? What task did I mention of the special ones? The one that does file integrity checks. Yeah, AMDF, I think, or something, or something like that. But anyways, the thing that does file integrity, you actually still don't want root to circumvent that, because then you could load a kernel module as root that has no signature, and then that circumvents the whole system. Cool. And then check the threads. So then you go through each of the threads in the thread list, figuring out if the, oh wow, okay, so it's, okay, so it looks like, huh. I wonder if there's a, no, probably not. But anyways, so interesting thing, this is why they have to do it for both. Okay, so this if config macf, it's not actual insanity that we're looking at here. There are reasons for these things. So what they do is, if you only ask for threads, what they do is go through all the tasks and check if you can execute, like, can this task be returned? Then, rather than going through every thread and then figuring out which task it is and then calling again into this macf thing of seeing if that task can be used, they use the list of tasks that they've already done and cull them, and then just iterate over their own list of tasks and say if it's left, that means it's usable. And that's why they have to, if they're doing threads, they also have to allocate memory for tasks and collect all the tasks. So it's not insane. I mean, it's insane to write code like this. Like this is like literally what my old professor, when I was a computer science student, said, never put an empty else statement here, because it's like impossible to reason about. So I literally never do this. I always use curly braces. But then to see it around a pound defined is like also bonkers, because like if you're not looking carefully, you would not like see this. Like these are not indented. Anyways, it's super interesting. So yeah, even if you're needing threads, you have to get tasks, because you check all the tasks first, remove all the non-allowed ones. The only ones left are allowed, and then you go through threads and you see if they're in there. If they're in there, then they're good. If they're not in there, they're bad.
So I think with this, we want to get the critical kernels and the kernel, but it's everything else you can right?
Say again?
Right? So with this, we can't get the kernel thread and critical process, but everything else you can get. So essentially, we can write the process.
Yes. So yeah, as root, we can get access to everything, right? So everything that's not that Apple, like the OS protects, but they're not going to protect third-party stuff. So if you have like a security monitor thing, you could get the thing for that. I wonder, the question would be if there's, no, I mean, that would not be possible. I was wondering if there's some kind of like race condition or something here, but no, I don't think. Because I think you have this, because we're not checking the threads, like is it possible for a thread to be part of a task but not actually resolve here correctly, or the task somehow changes, like it was allowed but it exec VEs into a new task that is not allowed, but you have the thread pointer to that? I don't think it works like that, but that would be an interesting.
I don't know if the lock actually locks.
Correct. Yeah. Yeah, exactly. Because there is a lock being held here, even through all of this, right? No. Okay. Yeah, the lock on collecting the tasks and the threads. So yeah, we'd have to look at what that collects. But that would be my one thought of a possible vulnerability. Like, is it possible to like get into this weird state where a task is allowed, but the thread is not allowed, or the thread very soon the task won't? Yeah, we don't know exactly what happens with exec VE with all this, but this is a very clear security thing. Cool. Okay, that was actually fun. And we found the thing right away. It's right here. Okay, if we didn't return anything, then just say nothing. Otherwise, return the things. If we allocated too much, must copy. That's interesting. Cool. Great. Okay, we're almost done. Yeah. So then, exception ports. So I kept talking about exception ports. So there's actually and like, again, the Mach part of the kernel is kind of the controller here. So when an exception occurs on a task, the very first thing that happens is the thread exception port gets sent a message to. Like the thread that the exception occurred on. And then either that port is dead because that thread died, or there's no message returned, or I don't know exactly the mechanism. But then if that's not handled, then the task exception port is sent a message. And if that is not handled, then the host exception port gets sent a message. And launch D, the main like process 0, like PID 0, or sorry, PID 1 gets the exception port. And this is what triggers then the crash dump and everything that happens to it. And this can happen because the exception handler, with as part of the port that it gets a task port for that killed, or a thread port, I can't remember which one, but gets one of these ports that can then read memory, modify the system state, modify registers. It can try to restart it and put it in a good state and then start the task or thread again. There's also, like, as long as the message is, the task is in like a suspended state, so it's not running. And so as long as whoever is receiving that exception port that can like read that message, it has all the time in the world it needs to do whatever it wants of like checking that process. So this is actually how there's companies that implement custom like crash analytics and these type of things. They use this mechanism, which I think is fairly unique. Like, I don't know that this necessarily exists on other systems where you can just say like, yeah, this other process can debug me, sure, but it can handle my exceptions for me too, which I think is pretty interesting.
I mean, I guess it does fall in line with what Matrix allows you to do, like catching signals still.
Yeah, but I wonder, I mean, you can't, there's no mechanism to say, I want this thing to p-trace me. You'd have to give that thing root privileges so it can p-trace anything. But like, I can ship an application that uses its own custom crash analysis library that sends me crash reports or whatever, that's completely unrelated to Apple's built-in stuff. So yeah, anyways, I think that's kind of a cool, nifty feature. Yeah, so this is a lot. I don't want to, we're at the end here. I don't want to dig into this because that was a lot of digging we did today. But yeah, I think you learned a lot. This was fun. Any other questions on important ports? Okay, we're gonna have a module on this. Like, basically imagine you get these ports that I've been telling you about, and then you have to get the flag. I think it'll be cool. All right, goodbye stream. I have 3 comments the whole